Hello! At this seminar, we will discuss convolution neural networks. And we will start with analyzing one-channel images in grayscale. So we will use for this task dataset that calls MNIST. It is the dataset that consists of handwritten digits. So we need to import necessary libraries. Then we need to create data loader. The batch size of our training dataset will be 64, and batch size of our test dataset will be 1024. We will apply such transforms as transforms to tensor and normalize. Okay, MNIST, and here we are creating our data loaders for train and test datasets. Shuffle is true. Okay, nice. Let's look at the results of our datasets. Okay, nice. This picture is 8. You can see it here. Nice. And let's look at the second one. Nice. This is okay. So at first we will use fully connected neural networks for this task. It will consist of 3 fully connected layers. As we are working with one-channel images in grayscale, the input size of our neural network is equal to the number of pixels of our picture. The images of MNIST dataset consist of 28 by 28 pixels. That's why our input size of the first layer, of the first fully connected layer, is 28 in 2 power. Okay, and we want to get 64 neurons as output. Then we apply the second fully connected layer. The input size is 64 respectively, and the output size is 64 to, and the last one 64 to 10. Because in our MNIST dataset we need to classify the digits. So there are only 10 digits, we know, from 0 to 9, 10 outputs respectively. We need to convert our image to a one-dimensional tensor. We will do it with the function that is called flatten. Then we apply our first fully connected layer. Then we apply Lickey-Relu activation function for adding non-linearity to our solution. Then we apply second fully connected layer, then Lickey-Relu, and then third fully connected layer. So after this, we need to return the output, and it will be the numbers from 0 to 9. They will describe the belonging to the certain class of digits. For example, output 4 is equal to the number 4. So let's do it. Okay, nice. We define our class. And now we need to define our train and test functions. In this example, we take a device as argument. It is done to copy the data we use to the place, to the device that we are using. So, for example, now we are using GPU. Let's look. Yes. T4 GPU. So that's why our device will be GPU. We can check it. Nice, CUDA. So here our data will be copied to the GPU. Next steps we have already learned. And we need to return our train loss. through the batch. Yes? So I want to say some words about function train. So there are some modes of our model: train mode or evaluation mode. And they are applied in different situations. For example, if you need to train your model, you should apply train mode. If you want to test your model, to test how it works, to calculate metrics, you need model.evaluation, because it's said to the model that there is no sense in calculating the gradients, because we don't need them when we need evaluate the model. Okay. So let's determine our training params. Learning rate will be equal to 0.01. Momentum will be equal to 0.5. Device CUDA, yes, because it is available now. And model will be our model, will be the object of this class. Yes, we want fully connected neural network at first. And our optimizer is GD with momentum. So let's train and look at results. Here we have 3 epochs. So there is calculating the first one. After this epoch, the test is here. And accuracy is equal to 92%. So it's good results. Let's look how it will be increased or not in the next epoch. Nice. 94. Okay, 94 too. So here we can see the graphs of train process and the graph of testing process. Let's now look at how our neural network looks like. Here you can see at layers, and you can find out how many parameters are in each fully connected layer of our neural network. You can see that number of parameters is really huge, and here total params 55,000, and all of them are trainable. This is how we can look at the parameters of our neural network. Here is a structure. Okay, and what result will we get if we will use convolutional neural network for this task? Here you can see that at first we need 2 conv layers, and they are applied by function conv2d. So here you can see this function, and there are some arguments, some important arguments that we will change for the better quality of our learning process. Input channels, number of input channels, number of output channels, kernel size, stride, padding, dilation, bias, and padding mode. All of them are useful. We were talking about them in the last lecture. And here we can specify our device. So, as we are working with 1-channel images, the input size, the number of input pictures is equal to 1. And then we want to get 10 feature maps. We want to get them with using kernel with size of 5. And parameter of how this kernel will move across the image stride will be 1. Let's look at the second convolutional layer. As we have 10 feature maps from the first layer, the input size, the number of input pictures feature maps will be equal to 10 too. And then we want to get 20 feature maps as the output. We will use the kernel size of 5 and try it equal to 1. What we are doing here, let's write something. Our pictures at first consist of 28 by 28 pixels. That's why at first we have something like this. Then we apply our first convolutional layer. As the size of our kernel is 5, each dimension of our picture will be decreased by 4. That's why we will get the feature maps of the size 24 by 24. So then we can see here what we're doing after this. We apply max pooling. So the pool size is equal to 2 by 2. That's why after this operation, the size of our feature maps will be reduced to the size 12 by 12. Then we apply ReLU function. It doesn't change the size of our feature maps. Then we use the second convolution layer, and the kernel size is 5 too. That's why it will be decreased by 5, and we will get the feature maps of the size 7 by 7. And then, 8 by 8. And then we will use max pool 2. That's why the size will become equal to 4 by 4. Yes? Okay, the resulting feature maps will consist of 4 by 4 pixels, and their size will be equal to 20. So the size of this fully connected layer will be 4 multiplied by 4 multiplied by 20. And it is equal to 320. Yes? 80 multiplied by 4. Yes, 320. Nice. That's why the input of the first fully connected layer is equal to 320. Then we want to get 50 neurons as the output of this layer, of this fully connected layer, and then apply the second fully connected layer to get 10 neurons as output, and it will be the resulting neurons that will contain the result of our neural network works. What's more, here we can see this function, conv2drop. Let's look what does it do. So, okay, here we can, is here, drop down, drop out, 2D. And this means that our neural network, while train process, it can zeros entire feature maps for increasing the quality of training process. It helps to get better results. And here you can find every function that is used in our Jupyter's notebooks, because we are working with Torch. And this is the documentation of this framework. Let's delete this and apply our first CNN. Okay, here we apply x.view for flatten our tensor 2, as we are doing here. Here, yes. It is the same operation. So let's train our new neural network, and I want to compare the results of this training with the results of training of fully connected neural network. Then I would like to compare the number of weights and the structure of our model. Okay, where here, yes. Okay, accuracy is equal to 90%, and it is worse than the first step of fully connected neural network. The second one, accuracy is equal to 93%. Yes, it is worse too. But what about the third one? Okay, 94, and here 94 too. So after doing these training processes, we can see that the result doesn't depend on the neural network that we use, convolutional neural network or fully connected neural network. But the reason of it is using one-channel images in grayscale. Let's look at the next dataset that consists of 3-channel images. And this dataset is called CIFAR10. But before that, we need to look at the number of parameters of our convolutional net and compare it with this. So here, 55,000 of parameters. And in convolutional net, only 20,000 of parameters. It means that the training process is easier, is quicker for our convolutional neural network. It is the main reason why we are applying this kind of neural network for CV. Not main, but one of the reasons why we do it. Let's look at our new architecture. Yes, it is bigger, but it contains less number of parameters. So let's go to the next one, to the CIFAR10 dataset. It contains 10 classes: airplane, automobile, bird, cat, deer, dog, frog, horse, sheep, track. Let's look at how our data looks like. Byte size of training process, of training set, byte size of test set. Okay, here we are creating the data loader. Then I want to show you how these pictures look like. Oh, why? It's like this one. Let's do it more time. Okay. Okay, now it's okay. Let's look. You see, this, for example, car. And tensor 1, because automobile is the second class. The first class is 0 class, and the second one is the first class. That's why here we can see tensor 1. Okay, let's apply the fully connected network for this task too, and then compare the results of this fully connected neural network with convolutional neural network. Here, the picture contains of 3 channels, and that's why the number of pixels is multiplied by 3. And the output consists of 500 neurons. Then 500 neurons to 50 neurons, then 50 neurons to 10 resulting neurons that will describe the solution of our problem. Okay, forward. flatten for convert our tensor to one-dimensional third tensor, then apply fully connected first, then Licky-Relu, then fully connected second, Licky-Relu, fully connected third, and then logs of max. It is done because we want to, the result will be in range from 0 to 1 respectively, and return it. Okay, nice. Let's look at train and test functions, but they're similar to that one that were used in the previous task. That's why we will go further. The learning rate is equal to 0.03, momentum is 0.9, device CUDA, model CNN, our fully connected. It's not CNN, but it's just the naming. And optimizer will be SGD. Let's try to start the train process. The num of epoch is increased here because we are working with 3 channel images, and the analyzing of these entities is more difficult, more slow. This is our first epoch. And loss here. Only 34%. Bad result. But this task is really harder than the previous one, because there we have grayscale images, and there we had digits. It is easier to classificate the digits. And here we need to do it with really complicated classes like airplane, automobile, bird, cat, deer. That's why the results will be worse than in the previous task. You can see that accuracy is really small here. Oh, bad. It starts to decrease dramatically. Now 45, really bad. It's less than 50%. Okay, after training, I want to show you the summary, the architecture and number of parameters that are in this model. And here we need to write the input size of our pictures. Not input size for our model that are equal to the size of our pictures. One, two, three, 4, 5, 6, 7, 8, 9, 10, 11, 12. Just wait a bit. Forty-seven, but really bad. The last one, I think. Yes. 15. Oh, 48. It's really bad. And here you can see that the model starts to overfit. This process is called overfitting, as we have already learned. That's why the real accuracy number is here at 9th epoch. Let's calculate. 1, 2, 3, 4, 5, 6, 7, 8, 9 here. Yes, accuracy is equal to 46. It's bad. Okay, and let's look at, okay. Here we have 1.5 million parameters. So it's really a huge number and all of them must be trained. That's why the training process required a lot of time and computing powers. So let's look at our model. Okay, as we have already talked. So, and now we will use for this task convolutional neural network. We will have 2 convolutional layers and then 2 fully connected layers. Let's check why this number is equal to 720. So, at first, here, we apply our first convolutional layer. The input size is equal to 3 because we are working with 3 channel images. And the number of feature maps is equal to 10. The kernel size is 3, that's why our picture size will be decreased by only 2 pixels along each dimension. So in CFR10, raw pictures have size equal to 38, 32, yes, it is 32 by 32. Then decreased by kernel size, yes, we will get the size of feature maps equal to 30 by 30. Then we apply max pooling and pool size is equal to 2. That's why our size of feature maps will be decreased by dividing by 2. That's why we will get feature maps of the size equal to 15 by 15. Then ReLU activation function, it doesn't change the size of our feature maps. Then conv2 is conv2d and it apply kernel of size equal to 3. That's why we will have feature maps of size 13 by 13. Then max pooling, it will be 6 by 6 because it looks like here. It's equal to 6. Okay, ReLU doesn't change the size, then view. Okay, we need to determine this number. Let's just calculate it. Okay, the resulting feature maps have the size equal to 6 by 6. That's why the resulting size of our first fully connected layer will be equal to 6 multiplied by 6 multiplied by the number of feature maps. The number of feature maps is equal to 20. So this number is 720. Okay, nice. That's why this number is here. Okay, here we change the view. We flatten our tensor to one-dimensional tensor, then applying first fully connected layer, then activation function, then next fully connected layer, and then log_softmax. Let's look at training process of this model. I just delete these things. Okay, nice. We created this class, and then we need to 1, 2, 3. Let's look. Okay, 43. $51. Okay, this is only the fifth epoch. We will have 15 epochs at all. And already we can see that the accuracy score is really big, is bigger than 50%. And it's already better than the result of applying fully connected neural network. And then it starts to overfitting again, so it's the problem. We can try to increase the volume of our dataset, for example, for avoiding this. But in these tasks, we have certain datasets with certain number of images there. Loss is really small, but accuracy is not really big. But it is really bigger than in the last training process with the using of neural network, fully connected neural network. Okay, and it is the final epoch, I think, or not? Let's look. Yeah, it was the final. So, what we can see here, the accuracy, this accuracy, is false because overfitting, the process of overfitting, it began here at second epoch. So the real number of our accuracy score is near 57, 59%. We have discussed convolutional layers, convolutional neural networks, and let's just recall that the number of parameters in these neural networks is really less than in the fully connected layers. Here we have 1.5 million parameters, while here only 24,000. Let's go further. In the last lecture, we were talking about notable architectures. We were talking about AlexNet and VGG. So, in PyTorch framework, we can find them. So, AlexNet is in the directory models and it is called as AlexNet function. Yes, we will use torch CUDA, that's why we need to tell it to our model in this way, and then print a summary, for example, if we want to look how to look at architecture of this neural network model. We can see first convolutional layer, then ReLU, then max pooling, and the second convolutional layer. And the first one consists of only 20,000 of parameters, while the second convolutional layer consists of 300,000 of parameters, yes. And the next one consists of the more number of parameters and more, and this number is not small too. The total number of parameters is equal to 60 million. So it's really a lot of numbers. We need really good datasets. The volume of these datasets should be really huge. And what's more, we need good computing powers because this model will be trained in good way only if we will do it really slow and really long time. And it is only the first net we were talking about. It was introduced in 2012. And the next one, VGG, that was introduced in 2014. It consists of more number of parameters. You can see it here. More than 100 million parameters. The number of parameters in VGG is bigger is really bigger. We need to multiply by 2 the number of parameters in AlexNet to get the number of parameters of VGG. So that's why the computer vision problem is really hard, and we need really cool architectures for applying them, for working with them, for achieving good results. That's why there are a lot of tasks we need to do for achieving really perfect results of our training process. So that's all I wanted to say today. Thank you for your attention.